And so the next speaker is Gero from European X-Fair, and he will present Caribou with IMQP.
Yeah. Right. So can you hear me? Yeah.
I think so. Yeah, the stage is yours.
So Caribou goes AMQP. So I'm happy to talk about the replacement of our core communication broker and want to show you a bit how we manage that. So just very short introduction. Caribou is our supervisory control and data acquisition system at our Beamlines and the instruments at European X-Fair. We'll talk a bit about the communication basics, the struggles with our original JMS broker implementation, introduce a refactoring strategy we had, and the timeline, how we worked on that. So Caribou is a device-based communication via a message broker. So we have self-describing devices. Here in the middle, we have the message broker as a heart of it, and devices for equipment control, for detectors like cameras, devices for online analysis, data processing, for data logging, some system devices like our GUI server, which is the entry point for all GUI clients into the system. Not much managed, not part of this talk very much. So broker-based communication, we have some patterns. One is one-to-one patterns, so request-reply. So devices register methods as slots that are things callable from the outside. There's a request from somewhere remote going to the broker, which sends a message to the device in question, and which then replies nicely. There is also one-to-all broadcast, which is for system purposes only, so I will not go in details there. And very important, of course, is a publish-subscribe pattern. So where devices subscribe some of their slots with a remote signal, in this case, we have two devices which subscribed to a signal of this device. So when the signal is emitted to the broker distributes to everybody who wants that. In that sense, Caribou framework is completely event-driven and doesn't need any polling. So this works nicely with the broker, but so just more about Caribou. So we have 3 APIs. So C++ was some of the initial language of Caribou, and it's used for high-performance framework devices like our GUI server, data logging, also for digitizers, which have to pull out a lot of data, and some cameras. A Python-bound API, which has Python bindings on top of C++. We just refurbished this to use PyBind 11 as a binding library. But the communication is completely covered by C++, so you will not hear more about this in this talk. Then we have the Python mid-layer API, which is pure Python. It was an early use of the async IO library in this single-threaded multi-processing thing. So it's now nowadays the most popular API, not only for mid-layer devices steering the others, which where the name comes from, but in general. So how is Caribou used? We have Caribou installation, so it's one communication unit basically for one instrument, for example, where we have, for example, one instrument I've chosen 2,700 devices roughly running there, altogether with 400,000 properties. And I just checked in one moment, so the message rate to the broker was a bit about more, 1 kilohertz, and then distributed to other devices with 4 kilohertz. And we have about 13 such installations. So that very nice is this communication patterns, especially the publish-subscribe with the broker, but we had this implemented with the JMS broker and used the client library, OpenMQC, which is a C++ library, which was also directly called from pure Python in our otherwise pure Python mid-layer API. How is it handled? So each device subscribes once to a Caribou topic, so the topic then basically being the instrument, and the broker filters the messages according to information in the header, where the target IDs are in there. That also means that a message header carries the target information, and the signal subscription is basically not on the broker, but on the device emitting the signal. So all nice, but we pretty early discovered problems that we had. So the most severe and most long-lasting was the global message backlog. So what does it mean? So messages that are not consumed are kept on the broker until the broker knows this is done. But if you can configure a limit how many messages the broker can carry, and if the maximum is reached, then the only thing that in some way works is to refuse further messages. But that, of course, there's no communication, so there's a complete failure of a supervisory system, of course. So how can that happen? So we had badly behaving processes where the threads are creating problems, so then you have a kind of a backlog. Or also what was discovered here in already 2015 already, when we had many receiving devices running in a single process. So in this example, 370 devices, which all should receive, for example, 10 hertz of messages, and then it can't cope, although 3,700 messages per second are not so many, but with many receivers distributed, this didn't work. Then somehow we hacked in kind of a last rescue, some message drop for low priority messages of properties which update frequently, then you may lose here and there a message. So for example, here the distance is 4 hertz times 370 receivers only worked because some messages were dropped. But then we notice, there's a memory leak in the library we use for this dropping messages thing. And we notice our library is not very well maintained. So we reported this problem, and it took more than 4 years, and this report was implemented upstream. Someone finally took care of it. Well, most of these problems we worked around over the years, except occasionally having backlog from badly behaving processes. So we had to set up some close monitoring of this backlog, and then on-call staff had to hunt the process. We had tools for that to kill the process which was not doing well. Then it was fine. And well, if this happened during the night, then it could have happened or has happened a few times that we really lost communication, maybe once, twice per year, and could be then potential loss of hours of beam time. But we didn't like this threat of online calls for this much, so we wanted to work to improve that. So how to replace the heart of your communication is a bit delicate. So the communication is critical. So whatever we develop, we want to need to be switched back. So if we oversaw a problem that only discovers itself in production, so we would want to be able to switch back at any time just by changing an environment variable. Then, of course, if you have object-oriented languages like C++ and Python, you have some abstract class in there and concrete classes for the different protocols we experimented with, and then it's dynamically chosen from this variable what we do. So it was clear from the beginning this is a long-time project, and of course we don't want to have a long-lived feature branch in Git, which then diverges in some respect from what we do. So we want to, whatever we do, we want to keep, we develop further and keep the old system working and intact. And of course, in such a project for this critical infrastructure, you need tests. Tests, you can't do enough tests. So we are happy that we have continuous integration in our GitLab workflow with unit tests for our communication class, that we ran then for all brokers, all times. Integration tests also in the continuous integration, which are repeated well for the current broker and well not all of our other brokers, because that then takes so long for the CI system. And we also have a big test portal run by our test engineer, which is run for each release candidate and alpha releases and so on. And that's even beyond the framework, testing some devices, at least some minimal tests there, where we integrated also some stress tests for the things where we knew, well, these are the things that we really want to cover, high data rate and a message order, as you will hear. So the timeline is a long path. So already in 2015, we just saw these worrying rate tests. But in 2016, we had to release a Caribou version to commission the facility. The next year, the first instruments went into production, so we managed all this, but never been 100% happy. So in 2018, there were the first serious studies of alternative brokers. At that time, we favorized the MQTT protocol. It's But it took another 2 years before the official start of an internal project to investigate protocols. MQTT, as I said, was liked a lot in IoT applications, which were in principle similar. Computers talk to each other. AMQP, as a Wall Street proven protocol, was the other one. Soon after, we had at least introduced our base class in all the APIs. Then we worked on, and in May 21, we had the experimental broker support. But KVR, the MQTT, does not keep message order if the messages are sent in different routes, which is the case if you have signals and slots. You can't do that. And then we had complicated custom code to keep the order, which is also not so nice. So we are happy that later on we had an AMQP, and also Redis experimentally supported. When 2022, well, there was work on robustness and failover for cases of lost broker connection, but also other things are on the time and the way. And in March, we had the first instrument moving to this, and RabbitMQ Broker provides ready-to-use monitoring, and that we really had a smooth start, just like a normal Carbo deployment, all happy. So soon after, we could follow with our biggest control installation, where we had also regularly some backlogs. Worked fine. We found some race conditions that occasionally let things crash, but we were confident enough in December last year to deploy this everywhere, so JMS is history. But of course, story doesn't stop. Then we saw, well, even the RabbitMQ broker crashed twice. So on our IoT division, then we replaced some hardware which was a bit oldish and upgraded Rabbit on there. Since then, we have no problem with that anymore. But we also noticed that the failover, so meaning the loss of the broker connection and then the reconnect, did not work. We also saw, oops, spuriously, sometimes some subscriptions for signals are not there, especially in the case when we had many subscriptions taking place concurrently. Sometimes things crash if many things should come up at the same time in one process, so there was even the decision, well, to rewrite in C++ the interface again. Now with unit tests with really concurrency situations in mind, this could be released this summer and already has been deployed for the backbone, like GUI servers, data logging, and so on. We decided to postpone the failover to the next release. But there we are. Then we still saw somewhere in our monitoring, whoops, there are some queues growing. Now here in a view from the broker management plugin, that you had a few thousand messages on some queues. But luckily, well, this could be identified as a CPU problem of the processors running these devices with these queues. Was overloaded host, really a lot of things going on this host, or a single process of the mid layer, which is a single threaded Python thing. But luckily, although we have some queues here, there's no danger for communication in a full installation that we had in the past with a broker backlog, because we have limits on these queues set, so the problem, if at all, stays local. Performance reached is, in C++, about 20,000 messages per second can be received, and almost the same number sent. And also in a single process, we can send almost 10 kilohertz of messages from one guy, and the other 1,000 guys in the same process receive 20 hertz, no problem. That gives us a lot of contingency, because we are not beyond 1 kilohertz for a single process usually. Also, the mid-layer Python gained a lot, up to 2 kilohertz now. Sending and receiving is on the same foot, and you have to count together. And the nice side effect is now we have a pure Python broker client library in use, which would simplify in future the distribution of the Python API. So the Carbo control system communicates via message broker, and we had some deficiencies of the original use JMS broker, and the client library spotted early. But since replacing the core technology in a used system is delicate, we always need to be able to switch back. We really require confidence in our test coverage. So it took about 5 years from the first series starters to full deployment. But the effort, I would say, was really worth it. We have no global danger for communication in a Carbo installation. less emergency calls, higher performance, and even the RabbitMQ broker that we use for the MQ protocol is in principle ready for encryption, which we haven't tested yet, but that it's a promise there. Thank you.
Thank you, Gero. We have time for one question. Yes.
Hi, thanks for the talk. A popular tool for this kind of thing is Kafka, and you didn't mention it at all. Can you talk about why you chose not to use that? Or
we slightly discussed Kafka. Well, Kafka is for the high data rate throughput that we manage anyway differently. So the big data for images and so on we do in another way, not via the broker. So that's not the relevant there. Yeah, and AMQP was very appealing in the end because we know it's used in the Wall Street, so they must do something right. That gives confidence.
Okay, let's thank Gero again.